there's an important concept that comes up in quantum mechanics that does not come up in classical mechanics. And this comes up because in classical physics, it doesn't come up in classical exactly where a particle might be. In quantum mechanics, our measurement process involves determining these probability distributions. But there's a certain kind of probability distribution that is intimately tied into the measurement process and which forms an important part of our later developments in quantum theory. So I'd like to define that for you now. This is the concept of a pure quantum state. In some sense, if you will, all classical states are pure, and that's why we need, but not so in quantum mechanics. So we have to define this. So a pure, this is the definition, quantum state. Now, a quantum state is always pure if it's pure with respect to a certain observable, or it could be pure with respect to multiple observables. But we say a quantum state is pure with respect to, and I like to actually abbreviate with respect to, because this is going to come up for us a lot, so WRT. A quantum state is pure with respect to an observable. And now I'm going to need a name for my observable. So my generic observable I'd like to call O for observable. For us, this could be P or X or angular momentum. It's just a generic observable. It could be the Hamiltonian. It's just a generic observable that we're thinking about. So a pure quantum state with respect to an observable, right, always, okay, and this is the key, it always gives the same result for measurements of that observable. It always gives the same result, theta naught, and we'll call that result we always get. It's not theta, it's an O. It won't become confusing for us, but let's try to be careful. It always gives the same result, O naught, so some particular result that it always gives for measurements of O. So if we want to think about the concept that I'm describing, right, what I'm saying is if I look at the probability distribution of O as a function of O, right, it's going to be one of these very sharply peaked values. I only get a single value, O naught, and the probability then is 0 for getting anything else, right, and it's very high, of course, for getting O, and then it goes back down to 0, something like this, right here along these lines. Now, at first, this might seem a little contrary to some of our expectations from quantum mechanics, so I'd like to discuss an example, right? You might be thinking when we first talk about this about position, because this might feel like it violates some fundamental principle, such as the Heisenberg uncertainty principle. And but I hope to convince you that actually it really doesn't. So, say I wanted to create a pure state of position. How would I do that? Is that actually possible? And the answer is yes, I believe it is. So if I were to take, for instance, my particle generating apparatus, and I get my particle sealed in here and all properly calmed down to his ground state. And now what I'm going to do is I'm going to take a tiny little pin and poke a super tiny hole in my top. So let me try to draw that, like a super tiny hole in here, right? And then I'm going to measure, as my particle emerges from here, I'm going to measure, say this is the x-axis, I'm going to measure the probability distribution for where that particle will end up. And because I've poked only a super tiny hole, when the particles emerge and come to my x-axis, they will be, of course, if I put a photoplate here, I would find them only at this one particular value. And that would then constitute one of these, and that value maybe is x naught, right? That would then constitute one of these pure states. Now, you might be thinking, well, wait a minute, I can't have it so that the width of this state, delta x, is actually going to 0. Right, so here's like a width here, delta O, and I'm saying this pure state has really delta O equals 0. And you would say, okay, well, that can't really be happening because I do know Heisenberg, and that would mean the momentum spread in this particle which has to be at least h bar over 2 delta x, would actually have to be infinite. And that would produce some sort of a contradiction. And there is some truth to that to taking that particular position, right? But as we've discussed earlier, in physics, really, you begin to realize after a while that nothing is ever, of course, truly zero, or in this case, truly infinite, right? I mean, we can't actually have a particle with infinite momentum. If you think about it, right, a particle with infinite momentum would have infinite energy. And we know that can't happen physically, right? You could take all the energy in the universe and you could suck it out of the universe and juice it into your particle, right? And that particle still would have, because we know the universe is finite and has a finite amount of energy in it, right? That we suck all that juice out of the universe and juice up this electron or this particle, it would still have a finite momentum. So the spread in momentum can't be greater than that fundamental universal limit, which means then I can't actually ever get the delta x exactly down to 0. That's true, but this delta x then would of course be super tiny. So what we're really saying here when we're talking about a state like this is not that delta x is equal to 0. That's not quite what we mean by a pure state, right? What I'm trying to emphasize for you here is that this concept of pure states, a pure state, is really a mathematical idealization. It's a mathematical idealization just like the concept of a point particle is a mathematical idealization, right? If I have a point particle, you might imagine, well, what do I have in mind for a point particle? Well, it might be something like a grain of sand. And a grain of sand is a great, view of a point particle if you're walking around on the beach. But if you put that thing in the electron microscope, a grain of sand is a super giant boulder, right? So what we're really trying to say here when we're saying something is a point particle is that it's smaller than all of the relevant length scales, physically relevant length scales that we're thinking about at the time. And likewise is true of a pure state. So they really are just mathematical idealizations of something that is not necessarily 0, but it's so close to 0 that it's physically indistinguishable from being 0. It's just not, its length scales aren't relevant. So if I give it an example of this particular distribution that I was sketching for you over here, just so we can think about this in a little bit more depth as an example. So if I write this probability of x versus x, and if I had such a pure state centered at x0, again, it would be a distribution where there's 0 probability here. There is some super peaked probability in here, and then now it goes down to 0. And what I'm really saying here is that not that delta x, strictly speaking, is 0, but that it is much less than any relevant physical scale. That's what we really mean. And if you think about it, there is actually a minimally relevant physical scale in our universe. It's something called the Planck scale. And this is kind of an interesting story. So the idea for the Planck scale, it's something below which no details of the shape of this function could matter. So if we want, we can imagine this probability distribution actually being a fully continuous and smooth probability distribution, just that it's concentrated down at this length scale that is so small that nothing in the universe really could depend upon the details of how this peak is shaped over that tiny length scale. And that length scale, that Planck scale, comes about in the following way. You say, okay, if I localize something to a super small location in space, that of course means then there's associated with it a very wide spread in momentum. And as you guys know, a wide spread in momentum, that comes from Heisenberg. So Heisenberg gives us a lot of momentum. A lot of momentum through special relativity actually tells us there's a lot of energy. Special relativity also tells us that with a lot of momentum, there's going to be a lot of energy, and that energy itself is going to be associated with a very large mass. And then general relativity will tell you that very large mass will eventually create a black hole in this region with an event horizon that can be made to be bigger actually than this length scale you're trying to see things on, and then whoop, it's all like hidden from us, and we can't get at the information inside of that tiny black hole, right? So the details of what's going on at length scales less than the Planck scale can't affect anything physical. So what we want to do is imagine that we have these nice, continuous probability distributions that are mathematically very well defined, just their width is smaller than any possible length scale. So the lesson that we learn here for such a distribution for a pure state is that the shape, of course, doesn't matter, because the details of what are going on inside something like that Planck scale can't at all be relevant. But there's another important feature that we have to respect, and that is if we were to integrate over all possible values of x, this probability distribution of x dx, right? If you think about our definition of probability distributions from up here, that probability distribution times dx is the probability that we find our particle, right, in one of these histogram bins. And then when we integrate, we're adding up over all the bins, and that means the probability, we're adding up the total probability of the particle being found somewhere. So this probability has to integrate up to 1. And the last thing we want to point out is that the probability, right, when x is outside of my tiny region, so this is the probability for finding x, right, has to actually vanish or be extremely close to 0 for cases where the distance between x and that center point, right, are greater than this width, delta x, that we're taking to be less than any physically relevant length scale. Right. So there's a special name actually for mathematical functions that describe this. So mathematical distributions that come in this form, right, of this form have a special name, and they are called Dirac delta, lowercase Greek delta, Dirac delta functions, or really, they aren't functions in a strict sense, they're Dirac delta distributions. The way I've described them, they don't present any fundamental mathematical difficulties because it can be a continuous function in there. It's just localized on such a tiny scale that the details aren't relevant. They're called Dirac delta distributions, and the way we would write this particular distribution would be to say that the probability of x then is one of these Dirac deltas that is 0 everywhere, except that it integrates to 1. It's non-zero maybe over some super tiny length scale, but that Dirac delta function in this case was centered at position x0, so we would shift the standard Dirac delta, which is centered on the origin, over to x0 in order to reproduce our probability distribution.